So, like I said before class, I threw some what I think are appropriate memes for today because it is cold. It is very cold. It is single digits, at least for us. It's a pretty cold day here in West Virginia. One thing I will mention, though, in all seriousness, I will do my best to try and keep to our schedule as much as possible. I think because of, bless you, because of the pandemic, the university's policy in terms of like if we close is that, it's sort of up to the instructor to on how to make up material, and we can do asynchronous or synchronous learning on days where the university's closed because of weather. And I'm not saying I'm gonna do that every time, but I really want to try and maintain schedule for really one simple reason. I want you all to have your Friday before break off, and I want to. So in order to do that, I want to try and keep to our schedule as much as possible. So I'll play it by ear, but I do want to kind of move forward through things. Homework 1.1 is graded. All the attendance is up to date. One thing I'll note about homework 1.2, I actually had a couple students ask about this, and it was a very pleasant surprise. There was a question on homework 1.2 about what chapter was a certain topic was in the spec. And it was actually in 2 chapters. It was in one if you read the chapter, if you actually read the spec. And a lot of people did that and was asking me about it. I was like, wow, that's great. So I went ahead and counted both answers correct. So I was fiddling with that a little bit this morning on Blackboard to get it to work. I think it's working now. So I counted both correct. So that was really good. Okay, 2.1 is going to be assigned today. This is our first assignment that's not a quiz. This is one where it's like an uploaded PDF or what have you. I am totally fine if you all with the tablets and the devices just upload, calcs like that. That's fine. I have a lot of students who just download the assignment and write on that. As long as it's neat, that's fine. But these problems, again, I think hopefully there's a trend that you're noticing and that they're really short. These are short assignments, and I'm intending them to be. But today, what I want to do is actually, let's get into some steel design. So that's what we're going to do. Our first sort of real foray into actual steel design begins with tension members. Okay, so let me go ahead and pull this up and let's get started. So what we're going to be doing today, so our goal for today and for the next couple weeks is the assessment of a particular type of member in steel design. And namely, I'm talking about any element that is loaded in pure tension. So taking a piece of steel and yanking on it, okay? Where would you find these in the real world? Well, in trusses, right? In the tension elements in a truss. Braces and buildings. Those are sort of the 2 main places you would find them. Now, I will blanketly admit to you that of common elements in buildings, like beams, columns, what have you, tension members are, I don't want to say the least common. I think just about every structure probably has some form of a tension member in it, or most structures have some form of a tension member in it. But there is a reason why we're starting with tension members, because I want to begin the idea of teaching you all the process of design, so we need to start somewhere. And tension members, by their very nature, are fairly easy to design, or at least fairly easy to understand how they're designed. But more than that, I want to teach you how to start using this, okay, how to start using the manual. And if we start with something like beams or columns, where not only do we have to learn how to use the manual, but the math is a little trickier, the design process is a little trickier. It's like, let's start easy and then work our way up. And tension members is a very natural place in steel design to start. So that's where we're going to begin, okay? Now, we're going to go back to this definition of a limit state, okay? Remember, a limit state is a condition that we as engineers define that basically says if your loads or demand on the structure exceeds the capacity or the supply, capacity supplied by a given limit state, then we say the structure is no longer fulfilling its intended functions. And remember, we broke that up into 2 main categories, strength and serviceability. We're mainly going to be focusing on strength for the somewhat foreseeable future. And so we're going to be defining a series of limit states for tension members. Okay, at least on the strength limit state side, we're going to define 3 of them right now, or 3 of them over the next couple weeks. That's gross section yielding, net section fracture, and block shear rupture. But we're going to take our time on how to compute those, because there's a lot of stuff that goes into the background on how to compute these, and we need to take our time understanding that. So what we're doing is we're looking at members subjected to axial tension. This is our goal for the next couple of weeks. Okay. So again, they are among the most basic type of structural elements. And one of the reasons why I say this, why I say they're basic, is the difference between elements in compression and elements in tension is that elements in compression have a tendency to be unstable. And elements that are in compression like to do this thing called buckling, right? I think you've probably heard that term buckling before, maybe in mechanics and materials, but you have a column, you put load on it, and it gets sort of wobbly, and it suddenly kicks out and deflects. That sudden failure under compressive loads is called buckling. And tension members don't really do that. So the mechanics tend to be a little bit easier from an analysis and design standpoint. So I'm going to bring everybody up to speed on probably a very fundamental formula that everybody's familiar with. Sigma equals P over A, right? So what is sigma equals P over A? It is the stress that you get from an applied load over a given area. So you fluid folks think of things in terms of pressures. Solid folks think of things in terms of stresses. But when we're assessing whether or not an element fails, we tend to not originally think in forces, we tend to think in stresses. Instead of looking at a force, it's a force per unit area, okay? Now, when we do structural analysis, we tend to, structural analysis tends to yield loads. So basically what we do is we say, all right, let's come up with some limiting stress, some stress limit, and then let's multiply both sides by the area to figure out what our max load is. And what do we get? We get that. We get that whatever our maximum allowable load is equals some limiting stress times the area, how big the member is. Now, where do we get the limiting stress? Well, we're going to see that in a little bit, but that limiting stress is essentially a function of what grade of steel that we're looking at. We're going to have different yield stresses and tensile stresses for if we're dealing with A36 steel, A572 grade 50, A992, etc. The areas are actually going to be worthy of discussion, and these areas are actually going to be the main focus of today's lecture. Okay. But again, I'm really sort of trying to make the point that this is really easy. You have a bar, you limit the stress, it's got some area. The maximum load you can put on that bar is whatever the maximum stress is times whatever the area is. Okay? So let's talk about those areas a little bit. Now, whenever we're looking at a tension member, we tend to focus on really sort of 2 key areas. Okay? Now, you all have heard me say this before, that the secret weapon of structural engineering is a samurai sword or a lightsaber if you happen to be a sci-fi fan. And so what we're talking about is important sections through this member for which we limit stresses. Okay? Now, the first section is what we call the gross section. Now, the gross section is just a fancy term for the main body of the member. So if you ever look at any tension member in the real world, you're going to see the ends of the member are going to have some sort of connection to whatever it's connecting to, either through bolts or welds, or if it's an older structure, maybe rivets. We don't really use rivets anymore these days, and I'll probably talk about that a little bit when we get into connections later. But the ends of the member are going to have bolts or welds or something like that, but the main body of the member is just it's going to be pretty prismatic. Any section away from the connections is going to be pretty uniform. And we call that the gross section. The net section is the cross section that's through the connectors. Okay. Now, a couple notes about that. So if you look, I've got here the net section drawn here on the right. Tension members are usually symmetric. So whatever's going on over here tends to be the same thing you got going on over here. That's especially with tension members. In other words, like if I evaluate the capacity right here, I don't need to evaluate the capacity right here. It's all the same. The other thing is that I have drawn this section through a very particular line. I'm saying it passes through the lead line of bolts. I'm going to be a little fast and loose with this term today because it's not really going to affect the connections that we look at today. But when we come back on Friday and we start looking at staggered connections, the lead line is going to be a little bit more important, okay? All right, now, I want everybody to open their manual because I know everybody brought their manual today because everybody brought their AISC steel construction manual, the big old manual. Everybody brought their manual, right? Everybody brought their manual. I'm looking at the folks that didn't, and I'm just going to go like this. Put my finger, I'm going to go. All right. I want everybody to turn to chapter D. I know that some of you might still be waiting on it in the mail. I want everybody to turn to chapter D. So it starts on 16.1-32, and you're way in the back of me, like right a little bit further ahead. All right. So everybody, I want everybody to look at chapter D. If you don't have your manual with you, maybe try and spy on somebody's next to you. This is the section of the manual, or the section of the specification that governs the design of tension members. I kind of think it's worth looking at to sort of just get up to speed with how specifications are written, what they look like. It's really easy to wrap your head around this. This is a very simple chapter. I've included some snapshots here on the slide, but let me go through a couple things. So section D, so there's the very beginning that sort of outlines the chapter, and then there's a section D1 that talks about slenderness limitations. I'm skipping that for now because we're going to talk about that later. So let's get into section D2. So section D2 is the section that says, bless you, it says, here's how strong your member is, okay? So basically what this is saying is you can use this to predict how much load a tension member can withstand. And as long as the load is smaller than these numbers, the member is safe, okay? And so it says here that the design tensile strength and the allowable tensile strength, so let's dissect that a little bit. So it says the design tensile strength and the allowable tensile strength. The difference between the two is whether or not you are using LRFD or allowable strength design. So these omegas, these are just factors of safety as we mentioned before. Remember, allowable stress design is just taking everything and lumping it into one big factor of safety. LRFD is factoring the loads and the resistance separately. So this is what we're going to use. So the design tensile strength of a tension member shall be the lower value obtained according to these two limit states. And so we have yielding in the gross section, and we have rupture or fracture. I will probably use the term rupture and fracture a bit interchangeably. We have yielding in the gross section, and we have fracture in the net section. And basically what this is saying is that our nominal capacity equals the gross area times the yield stress for yielding in the gross section. And for tensile rupture, we have this term effective net area times the ultimate tensile stress. So there's a little bit baked in here, okay? So we've got the gross area, we've got this term effective net area. What's the deal with effective net area? Okay, well, let's go to D3. Okay, effective net area. The gross area, the net area of tension members shall be determined according to this. We'll talk about that here in a bit. The effective net area of tension members shall be determined as the net area times this term U, a shear lag factor, okay? What I will tell you is that for the first week or so, we're really going to focus ourselves with two tasks, how to compute that and how to compute that, okay? And if you can compute those two, you're pretty much all the way there on starting to assess tension members. So those two terms are really going to be the main focus of the next couple of lectures, okay? So what am I talking about here? What am I talking about? So I'm going to give you a conceptual formula for gross and net area, and then we're going to refine it later, okay? So if you remember, gross area is the main body of the member, and net area is where the connection is. So how do we relate the two? Well, in general, the net area is the gross area minus however much material you remove because of bolt holes, Okay, that's a real simple way of defining it. I'm going to add some more science to this over the next couple of lectures. But in general, this is how you relate gross and net area. The net area is the gross area minus however much material you remove due to the presence of bolt holes. So for example, if you had a member and you just welded the two together, like maybe with fillet welds, then the net area and the gross area would be equal because you're not taking any material away. Does that make sense? Everybody okay with that? Okay. Now, we need a more specific formula, but if we wanted to compute the net area, we need three things. We need the gross area, obviously, because in order to compute the net area, we need the gross area minus whatever, so we need the gross area. We need the thickness through whatever plate material we're going through, and we also need the diameter. And notice how I'm being a little fast and loose with the diameter here. Let me sort of explain. Now, whenever we compute net area, we're not really interested so much in the bolt diameter as we are the hole diameter. And there is a difference between the bolt diameter and the hole diameter. How many in here have ever done any work, like in a mechanic setting, worked on your car, worked on your parents' lawnmower, anything like that, with a wrench, okay? If you ever try and take a 1/2 inch diameter bolt and stick it through a 1/2 inch diameter hole, it doesn't work, okay? The hole itself actually needs to be drilled slightly larger in order to facilitate fabrication or erection, right? You have to actually have the hole a little bit larger than the bolt, okay? So for example, I have here, let's say this is a bolt, okay? I'm actually going to drill the hole a little bit larger, okay? I'm going to drill the hole a little bit larger. Now, that actually comes from a different section in the manual. That comes from Chapter J, the section on connections. But Chapter J says that if you have a standard bolt, a standard size bolt, standard size hole, for any bolt that's less than 1 inch in diameter, which is most structural bolts that we use in steel design, or at least the most common, that we add 1/16 of an inch to the bolt diameter to account for what we call erection tolerance. So erection tolerance basically means that we drill the hole a little bit larger so it can actually put the darn thing together. So if you have a bolt that is 3/4 inches in diameter, you add 1/16 of an inch, and that's your proverbial drill bit that you use to actually drill the hole for a standard size hole, okay? Now, to this diameter, we then add another 1/16 of an inch to account for the fact that if you've ever seen, drilled steel holes, that little bit of material right around where the drill punch through, depending upon how it's drilled, can be a little damaged. So the idea is that from a net area perspective, we actually don't count on this material being, this little lip of material, this 1/16 of an inch, being effective in transferring load to the rest of the member. So if I tell you that the bolt diameter is, say, 3/4 of an inch, to get the effective hole diameter, we add 1/8 of an inch to that. And the reason why we're adding 1/8 of an inch is because we're adding a 1/16 twice. 1/16 counts for the fact that we're actually drilling the hole larger to facilitate erection, and then another 1/16 of an inch to account for the fact that this little bit of damaged material is really not effective in transferring load to the rest of the member. Okay? Does that make sense? So don't worry, we're going to practice this here in a bit. We're going to employ this. But for us, the effective hole diameter is taking the bolt diameter and adding 1/8 of an inch. Okay? So far, so good? All right. I think the best way to go through gross and net area is to just do some problems. So let's do some problems. Okay? Now, I want to pull this up here. Let me get my keyboard out of the way. All right, so I have here a problem. We're going to compute the net area for this plate shown, okay? So I have here some info about the plate. I have that the plate is 8 inches by 3/8. And what I mean by that is it's 8 inches wide and it's 3/8 of an inch thick, okay? We have 3/4 inch diameter bolts right here, and I have a note here that 3/4 inches is the most common structural bolt that we use really here in the United States. It is the most ubiquitous. The others being 7/8 and 1, and again, I would say 3/4 is again, it shines above and beyond, at least in building design. In bridges, you might see 7/8 and 1 inches a little bit more commonly because of the nature of fatigue. You might need more bolts. Okay. The other thing I'll mention, this little symbol here is called a break line. So whenever you see this, what it means is the main body of the member continues this way. So the gross section of the member is out here. And while this doesn't really matter for today's examples, it will matter a little bit for Friday in terms of when you deal with staggered connections. Does that make sense? Okay. So what we're going to focus on is we're essentially going to try and compute the area through this section here. Now, in order to do that, we're going to do a couple of basic computations, okay? Now, remember, we said that the net area is the gross area minus area lost due to bolts, okay? So area lost due to bolts. And I see here some folks with some calculators. I might need your help on some of these calculations. Okay. So the first thing that I'm going to do is I'm going to compute the gross area. Okay, so the gross area is pretty easy. So it's AG equals what? How do I compute the area of this plate? I'm asking you. I'll scroll up a little bit. Make sure everybody can see this. Oh, I don't want it right there. So how do I compute the area of this plate? If it's 8 by 3/8. I promise it's not a trick question. What is the area? It's 8 inches wide and 3/8 of an inch thick. Just multiply them, right? So all we're going to say is that this is just 3 inches squared. That should be pretty easy, right? That's not very difficult, okay? Now, before we start talking about net area, let's look at the bolts. We were given that the bolt diameter is 3/4 of an inch. So if that's the case, what's the effective hole diameter? 7/8. We add 1/8 of an inch. Okay. So far, so good? All right. Now, so I need to remove the area lost due to the presence of bolts. Now, here's the kicker. What's the area of a bolt hole? How do I compute that? If I have a bolt diameter, how do I compute the area of that bolt hole? Okay, a lot of people are thinking pi r squared, right? That's a good guess. That's wrong, okay? And everybody's like, why is that wrong? Let me explain, okay? What we're doing when we compute gross and net area is we got to think 3D. We're thinking samurai swords or lightsabers, okay? So we are samurai swording or lightsabering through this, and we're looking at the area. So if you look at this in 3D, here's what it looks like, okay? So what it looks like is we've got something like this. So here's our plate, right? And so what we're doing is we're doing like here's a hole, here's a hole, here's a hole, here's a hole. And then what we're doing is we're cutting through where those holes are, right? So the area that we're removing is that, right? Like, let's think dimensionally, okay? This dimension here three-dimensionally. That's 3/8, right? This dimension here is 8 inches. Okay, so if I just look at the area of this rectangle, that's the gross area, right? So just to put some pictures to it, like this right here, that's the gross area. But this that's the net area. And the reason is that what I have done is I have removed these chunks, right? So my question to you, well, first off, let's just ask a simple question. How many bolt holes am I removing from the gross area to get to the net area? It's 2. So a lot of people, when they first think of this, they think, oh, here's the connection. I'm removing 8 bolts because there's 8 bolts. No. It's what's through the section, right? And how many bolts are going through the section is 2. So therefore, if we go to the net area, so the net area is the gross area minus 2 bolt holes. And what is the area of a bolt hole now? Say it again. 1/3. Now, how'd you get 1/3?
7/8 times 3/8.
So that'd be 7/3, right? Right. Well, let's ignore the numbers. What I'm saying is, it is the diameter times the thickness. That's what I'm saying, right? Is everybody okay with that? So if I wanted to compute the net area, it is 3.00 square inches minus 2 7/8 3/8. That is the net area. Okay. So what is that? Let's give it to me in 2 decimal places. Oh, I see why I said that. Never mind. 8/3, 7/3. Never mind. And I get why you said that. Never mind. I don't have my calculator with me. Anybody have an answer for me on this? That's fine. Give me 2 points. 2.34. Do I have a second on that? Okay, so that's the net area. Does that make sense? That this is how we would compute the net area, the gross and net area. Again, we're starting basic. We're starting easy, okay? I don't want this to be a very challenging. I want this to be easy. Yes, sir?
So is that not like are you not saying that's like a cylinder?
So what I'm saying, here's what I'm saying. Let me try it this way. So what I'm saying is, so it is true that, like, if you look at, like a main hole right here, that in order to remove, like from a volume perspective, you're removing a cylinder of material to get that out. Like I'm not disputing that. What I'm saying though is that if you take that cylinder, so like if you take a cylinder right here and you cut right through the middle of it, like cut a plane right through the middle of it, you're going to see that rectangle with the diameter and the thickness. That's what I'm saying. Does that make sense to everybody else? This is good stuff. I like this. Any other questions? This is good stuff. All right. Well, if that's the case, now I want to take this problem and ratchet it up just a bit. Okay? Now let's take this problem and let's do the next one. All right, so here's the next one. So the next one is I want to compute the net area for a W10 by 49. Okay, I have given you a little bit more of an isometric view, maybe one that's a little bit more in perspective so you can kind of see it a little bit more graphically. But we have here a W10 by 49. I have also given you 3/4 inch diameter bolts on this problem as well. So let's conceptualize this. In order to compute the net area for a W10 by 49, what is the first thing that we need?
The thickness of a 10 by 49.
Well, yeah, but I mean, in general, how do we compute net area? The net area is what minus what? The gross area. We need the gross area. What is the gross area of a W10 by 49? And how do you get that? You look it up. There we go. So we go to the very beginning. So this is sort of the purpose. We break out that AISC 16th edition steel construction manual. We open it up to the very first section. So we're in table 1-1. Okay. So table 1-1 in the very beginning. So let's do this. Let's look gross area. So what I'm going to do on the board is anytime I have a manual reference, I'm going to put it in green. So it's going to be 1- something. Has anybody found the W10 by 49? What page it's on?
28.
28. So what is the gross area of a W10 by 49? 14.4 inches squared. All right, do I have a second on that? Everybody else find that? Is there anybody that did not find it? Don't like get upset, or don't feel like you don't need to raise your hand. I want to make sure everybody's on the right page. Let's see. Everybody looks like they're on the right section. Good. There we go. There we go. Looks like everybody's on the right page. Good. Okay. So now what we're going to do is we're going to continue and we're going to handle this the same way. So we've got, first off, let's deal with the bolts. So we know that the bolt diameter is 3/4 of an inch. So the hole diameter, the effective hole diameter is what? 7/8, same as before. Okay. Now, let's remind ourselves, okay? So the net area is the gross area minus the area lost due to the presence of bolts. So we know the diameter of the bolt. How many bolts are we going to need to subtract from a section in order to compute the net area? So if I samurai sword or lightsaber through the net section, how many bolts am I going to go through? 4, okay? So therefore, if I wanted to compute the net area, it is the gross area minus 4 times the hole diameter, but times what? The thickness. But what thickness?
Flange.
The flange thickness. Exactly right. So we need a flange thickness for a W10 by 49. What is the flange thickness for a W10 by 49?
9/16.
All right, we need to have top. We need to have top. Okay. So somebody said, what was it? 0.56? 0.56. Somebody else said 9/16. Does anybody remember the difference between these two numbers? Why does the manual list 2?
One is actually rounding up.
Well, rounding up, but why is it there?
For drawing.
For detailing, for drawings, for AutoCAD. These are design values. These are drafting values. Do not use these for design. Always use the decimal values. Always. So therefore, we get this. And what is the net area at this point? Say it again. 12.44 square inches. Do I have a second?
Yes.
There we go. All right. Boom. That's it. That's basically net area in a nutshell. Okay. Let me correct that. I got a little wrinkle I'm going to throw into the mix on Friday, and I'm going to at least introduce that wrinkle so that you kind of understand it. Okay. Before I move on, does anybody have any questions about this? Okay. So I want to mention two things. So right now, what I'll say is like right now, I would say this is a fair mathematical expression for computing net area. Is that a fair statement? That really what we're doing is we're taking the gross area minus the sum of the diameters times the thicknesses. Okay? Now, this is so far. What we're going to do on Friday is we're going to change this up a little bit, and we're going to sum up the sum of what are called stagger factors. Okay? And I'll say for Friday. And I'll show you why here in a second. But this is going to come up on Friday. This is not going to come up on your homework assignment, which is due Friday. Your homework assignment is going to be very, very brief. Okay? Can I go ahead and jump away from this real quick? Okay. So let me jump away from this real quick. And let me at least show your homework. So this is going to be your homework assignment. That's due Friday, and so I'm giving you two shapes, okay? So I'm giving you a WT, and I'm giving you a another W section, and I'm having you compute the net area of each. Now on this assignment, I know that some of you might still be waiting on your manual in the mail, so I went ahead and gave you the dimensions on this one, okay? So there should, if you're still waiting on your manual, you should still be able, close this. You should still be able to complete the assignment. Let me close that. All right. Sound good? Okay. Now let me show you a little bit about the challenge we're going to have to deal with here in a bit, starting on Friday, and then we'll call it a bit early. Okay. So, like I said, so right now, this is our expression. This is our expression for net area. The gross area minus the sum of the hole diameters, okay? And one of the things I put in my lecture today is I said that this lecture is for parallel grid arrangements, or parallel bolt arrangements, kind of like a grid, okay? In other words, that this formula works very well if your bolts are arranged like this. But what if your bolts are arranged like this? What if they're in this staggered pattern? Okay. Well, I think before we get into the what happens if your bolts are staggered, maybe a more fundamental question is that we engineers try and keep things as simple as possible. So why would we do this? Why would we decide to take bolts and start staggering them up like this? Like why make things complicated? Well, the reason why we do this is essentially to increase the net area, okay? If you are changing the path along which these elements fracture, you can increase the area along the net section. So let's follow that thought through. What happens if you increase the area? Like if the capacity, if the nominal capacity is some limiting stress times the effective net area. Like this is the strength. And I take the area and I increase it, what happens to the strength of the member? It increases as well, okay? So let's follow that thought through. If I have a certain load, if I need to design a tension member for 200 kips, and I have a given member, I can increase the area without actually changing the member itself. So in other words, I can get more strength out of that member without any additional hit on my wallet, okay? I don't have to make the member beefier and buy more steel to get more strength. So I can get a more economical design by just taking the bolts and moving them around a little bit, okay? So I want to be clear that like this is done in the real world for a real reason, okay? We engineers don't make things complicated just for the sake of making things complicated. If we're going to do it, there's going to be a reason for doing it. Does that make sense? Now, the problem is that if you do this, you end up getting different diagonal failure paths. Like you end up doing this. And so we'll talk about more on Friday on what the lead line of bolts and so on and so forth is. But the long story short is that whenever you're dealing with staggered connections, you could have different ways in which the element can fail. And so what we do is we add these stagger factors to account for all of the potential diagonal bolt paths. I'm not going to worry about that today. This is totally a topic of discussion for Friday. But I want to sort of illustrate the idea that this is coming on Friday, that we are going to be adding a stagger factor for every diagonal failure path. Okay, I don't want to go too far down the rabbit hole of this because I want you to have a solid foundation on just parallel connections. So I've got a homework assignment for you that just basically regurgitates what we did in class today. That'll be due on Friday, and then on Friday we'll start handling this stuff, which is I don't want to say a little bit more challenging, but there's just a little bit more to identify and observe. Any questions? You get 8 minutes of your life back. I'm going to pull the QR code up one more time in case anybody missed it, but I will see you all on Friday, and please try and stay warm.